Hi, everyone. Thanks for tuning in. So today I'm going to describe recent work with Damek Davis. The paper is called High Probability Guarantees for Stochastic Convex Optimization. So the basic question we want to address is as follows. We're interested in a stochastic optimization problem, which is smooth and strongly convex. And we're going to be interested in the following question. Under what conditions and how can we obtain high probability guarantees for numerical methods? Okay, so setting the stage, let's just set some notation. So we're going to be interested in minimizing a minimizing an objective function big F, which is an expectation over a distribution over the population data Z following an unknown distribution P, which we can sample from, of a loss little f. And we're going to assume that the losses are L smooth and mu strongly convex. Okay, and as a result, we're going to define the condition number of this problem as just L over mu. So kappa, that's the notation I'll be using throughout, is L over mu, the Lipschitz constant of the gradient divided by the strong convexity constant. Okay, so typical algorithms based on either empirical risk minimization or streaming algorithms like stochastic gradient methods find a point x that is whose expected function value gap is smaller than epsilon using a poly 1 over epsilon samples. Okay, so that's the cost of such procedures. The scales polynomially in 1 over epsilon under the various further assumptions on the loss. And so the question we want to ask is, under what conditions can we take such a generic procedure and boost the expectation bounds to high probability guarantees, and what's the number of samples that are necessary? And as a baseline, we can always take an expectation bound and boost it to a probabilistic guarantee simply by Markov's inequality. However, there's a big price to pay, namely, given any procedure that satisfies an expectation bound, we can be sure that it will generate a point x whose function gap is smaller than epsilon probability 1 minus p, but then the number of samples, if we just blindly apply Markov's inequality, has to scale polynomially in 1 over epsilon p. And so the scaling poly 1 over epsilon is expected. That's what you get for expectation, but scaling poly 1 over p doesn't seem natural, and the question is, can that be improved? So can the dependence poly 1 over p be improved, let's say, to be logarithmic in 1 over p? Okay, and so the real question we're interested in, what is the true overhead cost of high confidence? Given an algorithm, a generic procedure that gives you epsilon optimal points in expectation, what is the true overhead cost of boosting its confidence to be on the order 1 minus p? Okay, or more formally, so let's now make this a little bit more formal by declaring what we mean by an algorithm. Okay, so what we should assume is that an algorithm is really an oracle. So for every epsilon, we have an oracle, the algorithm. It will output a point x epsilon. And what we're going to assume is simply that it will output a point x epsilon that succeeds with fixed probability, let's say 2/3. Okay, better than a flip of a coin. It will find the point that's epsilon suboptimal with probability 2/3. And the cost, well, denoted in this way, C sub m, cost C sub m. M is going to be the algorithm. So in particular, the algorithms I've described that I've alluded to on the previous slide that give you expectation bounds by Markov's inequality immediately gives you success with fixed probability, 2/3. Okay, so the question now is, can we boost? What is the cost, the true cost of boosting the 2/3 probability to be 1 minus p? And in particular, maybe the ideal thing that we would really we would guess should be possible, perhaps, is to have an algorithm that maybe repeatedly calls m sub f of epsilon, and the total cost to obtain the high probability guarantee should only get amplified logarithmically in 1 over p. So that's the dream, right? That's the goal. And the question is this possible? And the answer turns out to be yes, essentially, almost. Okay, it turns out that in this very, very general setting, without any with no extra assumptions about what the algorithm, what m sub f is, we will be able to see that it is possible to indeed have a high probability guarantee to boost the low probability guarantee to a high probability guarantee, and the total cost will be roughly the same as the cost of a single run of the algorithm, but you'll have to multiply slightly by log 1/p, okay, and log kappa. So that's the overhead cost, and you need to rescale epsilon by log kappa. So up to logarithmic dependence in the condition number, you in fact do get a positive. It is possible to get a positive answer to this question. Okay, so what I'm going to do now is I'm going to describe how one can do this. Okay, so the goal is, given any algorithm that succeeds with fixed probability, how can we boost it to high confidence? Okay, and essentially, and what we're going to be using is strong convexity and smoothness of the objective. That's going to be very important. Okay, so let's start with a naive attempt, and then we'll discuss why it's not a great idea. Okay, so one naive attempt may be simply to generate just a bunch of points, x1 through xm, by independently rerunning our algorithm. So rerun our algorithm m times, lil m, and I'll use this notation throughout lil m. So we're just going to rerun it m times. We know that each of those points, x sub I, independently of others, is going to be epsilon optimal probability 2/3. So one of them is going to be epsilon optimal with very high probability. So we can compute the minimal value in principle and output the point that has the smallest function value. Now the difficulty, of course, is that you need to evaluate the function value at least to epsilon accuracy. And evaluating the function value is mean estimation. You need to estimate the mean of a random variable. And even under sub-Gaussian assumptions, evaluation of the function, which is mean estimation, typically its cost at sample complexity scales like 1/epsilon squared. And that cost can be significantly larger. The 1/epsilon squared can be significantly larger than the cost of running the procedure just once. Okay, so it may, in many interesting cases, we're going to be thinking about the cost of a procedure scales like 1/epsilon, and just evaluate that's a procedure finding approximate minimizer. But the cost of certifying that a point as an approximate minimizer by evaluating, let's say, the function value, only would scale like 1/epsilon squared. Would require 1/epsilon squared samples, which can be significantly higher. Okay, so that doesn't quite work. There is a fix to this. Okay, the fix is based on this idea of robust distance estimation. Instead of and I'll describe this in a second. So it avoids the question of evaluating the function. We will see, however, that it incurs a big cost in terms of the condition number. Instead of epsilon, it's going to incur a big cost in terms of the condition number. And then the key insight of this paper is to show that you can then alleviate this cost by embedding this robust distance estimation technique within a proximal point method, and that's going to be the full procedure. Okay, so that's what I want to do. Okay, so the first naive attempt does not work. So instead, the idea is not to evaluate the function value, but instead compare the points x1 through xm to each other. Okay, so why is this an interesting idea? Well, first of all, if in fact x epsilon returned by our algorithm is epsilon optimal, then by strong convexity we know that x epsilon is going to be close to x bar. Okay, so x bar is the minimizer. Okay, so let's call this this closeness parameter delta. Okay, so this means that all the points are going to be very, you run your procedure m times, all the points independently with probability 2/3, each individual one is going to be delta close to x bar. We don't know where x bar is, but this means that now the points are really going to cluster, many of the points are going to cluster near x bar. And so what you can do is you can now look at pairwise distances. Okay, so the robust distance estimation technique is then this very simple procedure which does the following. So it generates y1 through ym just by running the oracle. Okay, and now we don't evaluate the function value at y1 through ym, but instead what we do is we grow out a ball. So just in this picture, keep growing out a ball around each individual point y1, y2, y3, etc., until this ball has the majority of the points, so m/2 points. Okay, and then you just output the point whose radius, corresponding radius, is small as possible. So it's like a clustering technique, and so that's the point. So in this picture, that middle point is going to be with the red circle, corresponding to the red circle, is going to be the point that's output. And the classical result of Nemirovsky-Yudin and modified later by Su and Sabato says that as long as you only need to run log 1 over p trials. So m is the number of times you need to rerun the work. You only have to do that log 1 over p times, and then you will be sure that the point that's returned is close to x bar, delta close, with probability 1 minus p. Okay, so you've now boosted the probability of success from 2/3 in terms of distances at least to 1 minus p. But now the problem is that if you go back to function values using smoothness, what's going to happen if you just do a little computation, you'll see that the probability that the function gap is smaller than kappa epsilon is going to be 1 minus p. So what you incur is a condition number cost in epsilon, which can be very large. Again, so the question is, can we remove this dependence on kappa from the robust distance estimation technique? Okay, that's the main question we want to we're going to address, and the answer turns out to be yes. So the idea to remove the dependence on the condition number, is as follows. Instead of just running the robust distance estimation on the function f directly, so again, robust distance estimation just means you rerun the oracle on the original function f m times, and then grow out these balls, etc. Instead of just doing that once, what we're going to do is we're going to apply this robustness estimation to a short sequence of perturbed problems, slightly perturbed, and they're going to be slightly perturbed in such a way that the conditioning keeps improving. So we keep incurring a cost of the condition number, like I mentioned here, but we're going to alleviate that by trying to apply this procedure to better and better condition problems. Okay, and so the procedures then of course we call proxBoost, and what it does is as follows. You begin by simply declaring x minus 1 to be the robust distance estimator on f. So you do whatever we just described once, but then you don't stop. So then what you do is you, in tth iteration, given an iterate x sub t, you define xt plus 1 as follows. You're going to let xt plus 1 be generated by a robust distance estimator, but on a slightly different function. That new function is the original function, plus a quadratic perturbation. So the quadratic perturbation has centered at the current iterate xt, and the amplitude, okay, the amplitude of the quadratic increases very fast. So it's mu times 2 to the t. So it's geometrically increasing. That means you only need very few iterations in order to make the condition number of this function a constant 2. And at the very end of this chain, you don't pay anything. Of course, the question is, what have you paid in the middle? Okay, and so what we showed is the following. If you simply set m as before to be log 1 over p, so the number of reruns within a single robust distance estimation is only logarithmic in 1 over p, and the number of rounds of the robust distance estimation of the proxBoost, number of rounds, is only logarithmic in the condition number, then you in fact do get a high probability guarantee. And the high probability guarantee reads as follows. The function gap at the end, at x sub t, is going to be smaller than epsilon up to a logarithmic factor in the condition number, with probability 1 minus p up to a logarithmic condition, up to a log of the condition number. So in other words, you obtain the high probability bound that we were after up to a logarithmic factor. The overhead cost is only log 1 over p times log kappa, right? It's m times t. M is the number of reruns within a robust distance estimation, and the number of epochs of the proxBoost is t. Okay, and that's all. And as you can imagine, because this is so general, there are many consequences for both for streaming and online procedures, and so in the next 2 slides I've outlined consequences for what happens if you just pair proxBoost with an accelerated stochastic gradient method, and with empirical risk minimization. And what happens is then you can simply boost expectation bounds to high probability bounds at an overhead cost that's only logarithmic in 1/p and maybe polylogarithmic in the condition number. Okay. So let me stop here, and thank you very much.